session, and I think 3 lectures are left, if I'm not, including today's lecture. So I'll recommend I'll try to cover today till hierarchical RL and yes, I'll try to cover till hierarchical RL and the types of optimality. And then the next lecture, we'll try to cover the whole syllabus with the POM DP. I want to go in detail with the POM DP, though there are only 2 lectures there in the, will be taught there. But I think we'll go in more detail. It's an interesting topic. And then the last lecture, if visible, then we'll keep for the revision. So whatsoever you are having the doubt, or the topics which you want that we should discuss, we can discuss in the last lecture. Is it fine? Should I proceed?
Yeah, that sounds fine.
Wait a second, I'll share my screen. So I think he has covered till DQN. Am I correct? Or some things are left? I think he has covered the LSPI, which I left the last time, in deep Q networks. And he told me to start with the policy gradient. Is it fine, or some doubts are there till this topic?
That's correct, yeah.
Because he was saying that he has given just an overview afterwards.
Yeah.
So let's start. So whatsoever you are having the doubts, please write in the Slack so we can discuss in the further lectures, because 2 lectures are left after this. Or if you want that some topic should be discussed in detail, though in the next lecture, I'll discuss this POM DP, partially observable Markov decision process, in detail. It's an interesting topic. I want that some numericals or some coding part should be solved with that topic. Okay, coming to policy gradient. So what do you think? Which one is preferable? If I compare this value function with the policy, which should be preferable in the examples, or what are pros and cons of both of them? Yes, come on. Any idea, any rough idea? Sessions are going to end. I don't want this. I want the interactive session till end of the sessions.
Yeah, so policy gradient.
Yes. So, okay, by policy is preferred over value function. It might happen that value functions are preferable over policy. It depends on the problem. On what problems if you say that policy is preferable over the value functions?
So when the space is a lot more complex in case of value function.
Yes, I can say that value function becomes more complex in some cases.
Yeah, yes.
Can you give an example? I think it was given in inventory example,
Yeah.
normal examples, like sometimes policy, what is policy? It's just a rule, I can say, such as a, like, but if I have to say about value function, it becomes sometimes more complex, because you have to represent the expected total cost, or taking into account the future aspect as well, considering all the possible future space. Basically, if I talk about the value functions, as we have seen that we have to solve the DP thing, we have to consider, I can say, all possible future states, actions, then I can say the expected value of this cost or the profit under each scenario. So it becomes cumbersome sometimes because of such a huge state is there, or I can say a state space is there, or I can say sometimes the problem becomes so much huge that we are computationally, it becomes intensive, I can say. So can you first tell me, like, what is this inventory problem? Like as the professor told, like this is an example of the, like there's an example that in inventory case also, policy is preferred over the value function. Can someone tell me what is the inventory? Though we'll not discuss in detail, like what is inventory control problem? I'm not talking how to solve this problem, just what is the inventory control.
So whether to order some items or not. Really.
Yes. You're correct. Suppose inventory is basically like we are saying that, okay, whether to order some problem, like when, whether or I can say how much I should order or not, or I can say how much I should order, basically to minimize the cost.
When to order. When to
Problem.
order. Yeah.
When to order, yes. If I talk about with the perspective of value function, then I have to consider all the like it will include information about all future possible scenarios. Given the, I can say, current inventory level, how much you have in your stock, then it will consider all the future problems. If I talk about this policy, it will talk about best what you will take the immediate action at that point only, given what we know about these long-term rewards. So it can consist of like the problem can be solved, like suppose how much demand is there, how much holding cost is there, I can say how much, suppose unsold item, what is the sales cost, then I'll consider that whether I have to order or not. Then similarly, this goes like a value function, or it's good that it will be better option if I'll give a problem and then at the end of the lecture, and then let it be a homework problem of inventory problem only, and then you can solve like using the value function or policy, just a rough example, a toy problem, and then you can differentiate between them. Okay, now coming to this. So in some scenarios, as we talked about, that value function is better. Now coming to the parameterized setting. The second benefit is now, after looking at this, can you tell me what is the second benefit of using the policy over the value functions? Yes.
The professor talked about convergence. Yeah, convergence in case of value functions.
If I talk
And
about parameters, which one is taking more parameters? Can I say that policy can be represented with the fewer parameters than the value function? As I said that value function needs to capture all the relevant information about the future or the environment. Policy only needs to output the action to be taken.
Yes, madam. See, just policy includes only the actions to be taken. We have to only store the actions, not values. So
Yes.
it will be less memory intensive.
Yes, you are right. And he's also talking about the other benefits about the convergence. That the like, can you tell me who's like which one is giving me the better convergence behavior? As someone told about the convergence now only. So value function will talk about the like give me the better convergence behavior or the policy. Policy function or the value function.
Value function, madam.
Okay, what about others? What about other thing about that?
so pure parameters in case of policy. So chances of convergence is, higher than in case of value functions.
Yes, actually, because we are talking about the local thing. So I can say it can converge to local optima. We can guarantee that it will at least converge to local optima here, policy function. So that is why the chances of the convergence I can say is higher than the value function. It means this is simple. I'm saying that we have used it earlier also. Policy depends on the parameter theta. And I think, okay, now what I'm writing, we have done it earlier. When we were discussing about the policy gradient and the bandits thing. I hope you remember. First, I'll write about the bandit thing only. Then we'll just revise. Then we'll go to the next. So can you tell me, as we have done this equation and we have studied about this in bandit, about the policy gradient, now considering the bandit thing, like policy gradient in respect to bandit, so can someone tell me about what is this equation? Eta is basically the performance measure. Coming about Q star A, what is Q star A?
True value of playing the arm. A.
You're not audible. Like, can you repeat? You were not clear, basically.
Yeah, the true value of playing the arm A.
Yes, basically true value of playing, of getting or playing this action A. And what about this pi A theta?
Probability of picking that arm parameterized with theta.
Yes, basically now I am summing up over like what is the probability that I will take the action A when I'm selecting this action according to theta, or I can say parameterized by theta. What is this probability I'll pick this action A, and then what is the expected payoff or I'll get from this from taking this action A, summing up over A. So this is what we have already done. Any doubts in this equation? Okay. So I know this, I can figure out this or no? Can I calculate this eta theta or no?
Madam, that left-hand side, does it, it looks like a value function, right? Value. Okay, even though it has only one value, one state, but eta of theta looks like a value.
It's basically I'm evaluating the policy here.
Okay.
If you'll go and revise, I think it was week 3. If you'll open the notes there, you'll find the policy search or policy gradient we have done in bandits. There we said that this is the policy, how we are evaluating the policy. What we are doing is, what is the probability? Now here there are no states here because this is banded thing. As we have done in map, states are, we are not considering the states there. So according to theta, like I'm choosing this A basically. What is the probability I will take? I can say what is the probability I will take A according to this theta, and then what is the true value, or I can say true payoff after choosing this A. That is how I'm basically evaluating this policy. Now coming to is it can I calculate this whole term or no? Yes.
We don't know the true value.
Yes.
Yeah. Yeah. We don't know the Q star.
Yes. You both are right. We don't know the Q star A. So basically, we can't calculate it. That is what we have done earlier as well. So taking the gradient, we just write the whole term. This is just writing it straight away. It was whole derivation which we have done, like how we came to this point. In the week 3 lecture, or I think week 3 or week 4, you can go and here I have told about this in detail, that how we came to this. So what are we doing in this point? We actually multiplied and divided by this pi a theta, and then we got this expression itself. So as we can't calculate this Q star A, then what we are doing? Can I say I'm sampling it?
Yes, madam. We are sampling Monte Carlo.
Average.
Yes.
So that is what here is happening. And now coming to, this was the abandoned thing. Now coming to our thing, full RL problem. This is what we have already done. Now coming to full RL problem. How we sample? What are the samples here? I can say I have state is not A not action. Then I'm getting the reward. Then state. Is this covered by the other TA or no? Yes, can someone answer me? Is this covered by the other TA, these things?
No.
No.
Actually, he told me that he has already given the overview of all of these things till ectocritic. So this is what is the trajectory. I'll come to it just in a minute, what I'm writing. Now, can you explain me this equation? Like, I think you can correlate both of them. Can you explain what I have written here? Now, what is the performance metric here in the full RL problem? I have the whole trajectory which I am collecting. Now, what is this equation, performance measure? Yes, come on. go step by step and figure out what is it.
Is a value.
Can I say is it same as above one? Just we are taking the states here.
Yeah, we are taking a straight value here.
Yes, that is what we are doing. This is the return on the like I can say here in the place of that reward, I'm writing the return, what I'm getting on the ith sample. And starting from this, I can say S naught state, what is the return I'm getting? And then this is basically the probability of taking the trajectory here. That is what I'm mentioning here also. That is here it was like probability of taking the action, and here I'm mentioning what is the probability of taking the trajectory here. Or probability of, I can say, sample, I'm saying that starting from S naught and then taking the trajectory, that is what is it. Can I write this as so the above equation was that I'm taking the like what is the probability of taking the trajectory, and if I'm taking this trajectory, then what is the return I'm getting. That is what was the first equation. Now delta pi s naught theta, how this come? Just nothing, the gradient of ln when I'll do that is 1 by pi s naught theta, and in numerator the gradient of this pi s naught theta. Is it fine? Just when you take the gradient of this ln pi s naught theta, then this will go in the like denominator, and this then gradient of this. Is it fine?
Yeah.
Okay. Basically, in value function, we are saying that every state has different value. And here we are saying that the single value represent the entire policy. So basically over trajectories, we are taking this. Now, what are the assumptions we are taking? First assumption is we are having unique state. Can someone tell me the example when we are having the unique state? Any day-to-day example when we are having the unique state? Means we'll start from the unique state, I mean.
Means,
Yes?
yeah,
Any games, board games.
starting
Okay.
position where
You're not audible.
get unique positions, right? Start position.
Basically, start position is unique. As he told you, yeah, like board games. In board games, your start position is unique here. While
No,
in
No, madam, but even the terminal positions are also unique, right? In both games, start and terminal, both.
yes, yes.
Yeah.
Now we are saying that let us take the assumption where the starting state is unique, basically. So board games, as you told, the terminal is also unique. Okay, now we are focusing on the starting state, and the another assumption is this is our average reward, basically. Okay, if I say that average reward is this, does the state one, if I'm starting from state one or state two, the initial variations will matter or it will not matter? Whether I'm starting from state one or state two, will it matter or it will not matter if I'm saying about this average reward in RL?
It matters, right? The X might change. No.
Okay, what? Yes, yes.
This is average reward when the number of states increase.
What we are saying is whether we start from state one or whether we start from state two, does it matter or it doesn't matter? As we are saying that this is the average value and we are basically summing up to infinite series of numbers, limit n tends to infinity. So the starting state will not matter as we are going to infinite
Yes,
number of.
correct.
So I can say that starting from any state will converge to the same quantity as we are going, as we are saying n tends to infinity here. So regardless of whatever we start, we'll basically end up in this. Okay, and like we have also done the discount factor also, like when we are doing this, why we are doing this average reward RL when we have large number of like infinite series, I can say. Okay, now we also use the discount factor. So which one is better, whether to use this discount factor or whether to go through this average reward RL where we are taking this average and all? Why? What are the limitations with discount factor? Yes. We have done that discount factor is useful as a discount factor, basically like if we have infinite series, like, or we can see, we can give more weightage is given to the nearer one and far sighted lesser weightage is given. In that point of view, okay, this gamma is useful. When can gamma create some problem?
When
Sometimes.
when
Yes,
the
yes.
number of states, less. No.
In inappropriate selection of gamma is domain
Yes,
dependent or problem dependent.
yes. Actually, sometimes inappropriate selection, or sometimes gamma becomes, I can say, meta parameter also. Meta parameter means I want to get a result, so I'm tuning this gamma.
Hyperparameter.
Actually, it shouldn't be the case. We shouldn't tune it, I can say. It should be problem. If in some cases it's problem dependent also. In some places, gamma becomes a problem because we are making it becomes a meta parameter, or I can say, you are tuning your problem according to the gamma so that you can get the result. That is what. But now, what are the disadvantages of this average reward in RL? Are there a disadvantage of average reward RL, or it's a better choice, or is there any drawback using that also? Yes, come on. What do you think, that average reward RL is a better approach than discount factor, or it depends on the problem, or okay, someone is saying, okay, doesn't matter. Okay. Yes. What are your point of view about this? Any rough idea? What do you think about this? As we are doing it from a long time about this average reward and all. So what do you think? Is it better approach, or then discount factor because of this, or something is there?
No, as Professor has mentioned, no, it is better theoretical. It has better theoretical properties.
Yes,
Like
yes, you
that,
are
yeah.
right. But if I say about numerical, practical,
Practical, I mean, it might be difficult or might be hard to get.
yes, yes, you are correct. That practically it might be hard to get to work if we talk about average reward RL, because we have to go through all the trajectory, visit the states again and again, not to stop. So that is what in practical assumption sometimes it becomes difficult for us. So,
We have to consider n very large.
yes, yes. That is the thing, we have to consider n very large in that case. Now coming about reinforce. This also we have covered in the bandits part only. So as we have done this in bandits, can you tell me like what is it? Yes. Went to incremental version, then we studied about this delta theta n. Then we studied about reinforcement baseline. Characteristic eligibility. Yes, come on. Any rough idea? Just a gist about it, overview. Okay, what is this BN? Reinforcement baseline?
And the minimum reward that we need to get to update the parameter, right?
Yes, I can say that after BN, I can say they are good actions, or below BN, I can say that are bad actions. Is it so?
Yeah.
Can I say it's a baseline?
Yeah.
So how can I get to know whether it what should be this what should be this above this? I'm saying if it is a good reward, below this I'm saying the bad reward or bad action. Like what is it basically? It is basically the one way of doing is like I'm taking the average of all rewards. Above that, I'm saying that it is a good reward, and below that, I'm saying that it is a bad action, or I can say above that, I can say that is a good arm or good action, and below that, I can say that is a bad action. So now we are going to extend this idea to the full RL problem basically. Basically did the this incremental version, then we came to this thing in the bandits part. As pulling up as you know, what are the advantages of incremental version? I hope so. And then why we came to this this thing and then how this this characteristic eligibility is there. This is basically, can you tell me what is this? This is characteristic eligibility. If I'm saying basically term I'm giving. Okay, what is this? Basically, what is the theta I should choose that is more responsible for the change? If I say that choosing theta, which is more responsible for the change, I can say theta, which has the higher gradient, because gradient is what is like the change. And this whole incremental process, we call it as reinforce. Should I proceed? Okay. Now we are going to extend it to the full RL problem. Similarly, we'll write it as so as we told that Bn is basically, I'll write here, we'll take the average of all rewards. And if I'm writing this Bn of Sn, I can say it's average of all returns when I'm starting with Sn. Now coming to the sector critic part, basically, before jumping to it, what is sector critic? I'll give you a numerical example as well, just so that we can understand it more clearly. What is sector critic according to you? What is the sector critic problem? What is actor? What is critic? Before jumping to it, let us first try to understand intuitively. Let's go behind the intuition here. We'll not go to jump to this numerical method. First, we'll understand what is the intuition behind it. What is actor and what is critic? Yes, come on. Now, in this case, what we are saying, actor is basically one which represents the policy of the agent. It is taking the state as input and output giving as an action. Basically, I can say that actor is a decision maker in this case. If I say this Gn minus Bn Sn, basically this Bn Sn, if I'm saying this, this Bn Sn is nothing. If I'm saying that it is average of all rewards, when starting from like state n, I'm just referring to as Vn here basically. So this is my actor. I'll go in more detail about this actor critic, and this is critic. What do you mean by actor? I'm saying the policy here, and the critic I'm saying the representing the value function here. What I'm saying is represent the actor. Actor is one which is representing the policy of the agent, taking the state as input, output, giving the output as an action. It's a decision maker. And if I talk about the critic part, what it is doing, it is evaluating the value and say of taking a particular action in a given state. Or basically updating the actor policy, I can say. Anyone can explain me what I'm trying to say about this actor critic now? Someone can explain me what is this actor critic after this explanation?
Madam, it appears to me this is a nothing but evaluation of Q, right? Q value.
Basically, it's like I'm using both the policy function as well as both the value function. I'm taking the advantage from both the policy function as well as value function. I'm saying that I'm representing the policy in the form of the actor. Like I'm saying the actor in the form of the policy, and critic, I'm saying that I'm evaluating the value here. Okay, I'll take a toy example as well. Anyone else can answer, like can explain it better?
No, I don't understand the critic. See, the actor is nothing but a policy. Policy making decision is an actor. Okay. Critic means it is evaluating. This looks like similar to policy iteration, where we take a policy, iterate, compute value, and again improve policy. I don't know. It looks similar.
Policy function is also used, value function is also used.
Yes, yes. 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 Okay, go ahead.
Yes. What about others? Everyone understood, or can someone brief it out if someone understood it clearly? Yes,
So,
come on.
yeah, so actor is the one which takes an action. Critic is going to evaluate and generate all these value functions based on these actions.
Yes,
And
yes.
these value functions are used to update parameters of both critic as well as actor.
Yes, absolutely correct. That critic is the one which is going to evaluate the values, and it will be helpful for both the actor and critic as well. Basically, updating that, making the actor to make the decision, helping the actor to make the decision here.
Yes.
So the other question is here. I'm saying that actor is the policy and critic is the value function. Can it be reversed? Can the actor be the value function and the critic be the policy function? Okay, we'll see further. Yes. Okay, let's take a small example. Now, it's just like we'll just have the intuition behind it. We'll not run we'll not.
Yes, madam. Yeah, we can have actor as a value function. The optimized, the action which optimizes the value is nothing but nothing but the decision. Yeah.
We can take.
Yeah. Yeah. The action which optimizes the value is nothing but actor. Is the decision.
Yes, actually, yes. Actor is one which will make the decision based on the critic's value function, as well as it will update its policy here.
But the function approximation need to change in that case. Function approximation need to change. In that case, if I exchange the role of critic and actor.
Function approximation, if we change the role, okay, we'll see further. I'll change the role of actor and critic, then we'll get to this point.
Okay.
So we'll try to have the intuition behind it. I'll not solve the whole example, just it's more of intuition based. Imagine there is a robot and we are trying, the task is in a room basically, and the task is to make the robot learn how to turn on the switch. And the actions are basically try to flip the switch, and the other action is do nothing. State is basically either switches off, I can say it as 0 state, and either switches on, I can say it as 1 state. Now coming to actor critic. Actors policy. So suppose I'll say initially, I'll come to this episodes in a minute. Probability of flipping is 0.5 and probability of being idle is 0.5. And if I talk about the critics value function, switch off value, initial values are basically 0 here. Coming to episode number 1, just we'll see the intuition behind it, how it is solved basically.
What are the rewards?
Okay, let the reward be, I can say if actor decide, if it's flipping, then the reward be +1. And if it's idle, then the reward is 0. Okay, now coming to episode 1, basically. So suppose we are in the off state, the state is off. So actor decides to flip, basically. Suppose the action taken is through the policy, flip. And as I told that the reward will be +1. This was the actor thing. Now coming to the critic thing. Wait a second, we'll go through it. Now what will be the estimated value? As we said that the initial value is basically 0.
That is 1 plus gamma 0. Gamma
Plus gamma 0. You're
gamma
correct.
Gamma is what?
1. Let us take it as 1 only.
Okay, it's 1. Yeah.
So okay. Talking about the error.
1 plus gamma 0. Gamma into 0. 1.
Wait a second. Okay. Here we are doing bootstrapping.
Yeah.
Do you understand the word bootstrapping here?
Yeah.
Can you explain?
Based upon all possible next state, we are estimating the value of current state.
Yes. So basically, on the previous state, I'm doing the TD error here.
Correct. Yeah.
From the last state, from the previous episodes also, it will matter. Now I can say the TD error is reward plus gamma VS dash minus VS.
Yeah.
So what is the reward here?
1.
1. Gamma is 1. Current, let's take is 0 here. Okay.
1.
1. So we have 1 here, and now our value function is basically updated. Can I say this is the value function? This is the updation of the value function.
Yes.
Can I say this?
Yeah. Yes. So 0 plus 1.
0 plus, let us take this alpha as 0.5.
Okay.
So can I say Vs is equal to 0.5? Now, earlier my Vs was 0, it's updated to 0.5.
Yes.
Now my critic is giving me 0.5 as Vs basically.
Yeah.
Now coming to episode 2. My actor has now, what will happen?
What about updating policy? Updating
Yes,
policy is the actor in this episode 1 itself.
it's done. Now in episode 2, we'll do based on this value function.
Now, for actors policy in episode 1.
Actors, first we'll do act. Okay. You are correct. We'll update the
It
policy.
is updated both, no? At both ends, no?
Yes. So if I say about the policy, okay, you are correct that we'll update the policy based on the value function here. Value function is going to be 0.5.
Before updating whatever the TDRF, based on that we are going to update. Are we
Yes.
going to take updated values, or before updating just a evaluation? After evaluation, whatever are the values we are going to take, right?
Yes. So I can say that actor will update the policy. It will now value function is increased. Can I say that the probability of flipping will increase? Actor will basically increase the probability of flipping when the switch is off.
Yeah.
Can I say this is the policy updation?
Yeah. Yes.
So now what is happening is the main intuition is critic this value evaluation. According to this, as my policy is getting updated on the actor end.
Yeah. So can we compute by how much it is increased? Alpha,
Okay.
alpha, delta, and then it's a lookup table based method, no?
It is basically lookup table based.
Yeah. Yes.
Okay. Let's take alpha.
That is delta theta we are computing, right? The gradient of theta. It is alpha and delta and theta. Phi. Alpha and delta and phi.
Alpha, delta, and phi.
Yeah. Alpha is 0.5, right? Here also. Yeah.
Alpha is 0.5. Is it long?
No, only phi. It is, linear estimator, right?
Yes.
So, yeah. So that's why phi.
So what is alpha?
Oh, you have to tell. Alpha is how much?
0.5 we have taken basically.
0.5. Delta is 1.
Delta is 1. How this will be? What will be 5 here?
Yeah. So phi is, yeah. It is phi Sn comma An. So how do we represent phi here?
That is what I am also looking.
Yeah.
Phi.
Is it 0, 1 or 1, 0 like that?
Okay, let's take it as we are in the state 0 here.
Yeah. Yes.
And the action is basically the 0 here. Action flip. Let us take it as 1, and idle. Let us take it as 0.
Yeah.
So basically 0, 1 here. Not getting what will this phi thing.
So we have to assume the linear function. These are En attributes.
Yes. So we are basically assuming that this is basically a lookup table where we get the
Correct.
slipped off my mind. Now whatever, can we take it as 1?
No.
So we got.
Is it a vector? It is a vector.
I think it should be phi Sn An. If the value of 0, 1 lookup table is 0, 1, then it will given me 1. Okay.
It is gradient, right? So left hand side is gradient.
Left hand side is gradient.
So how many thetas are there? We have to first know the function, right?
Yes.
How many thetas are there?
So the parameters here,
So we can take 4 parameters. Say there are 2 states and 2 actions in each state.
So what are the states here basically?
States are 0 and 1.
0
Off,
and on
yeah,
or off.
on or off, yeah.
And the
action is
actions are flip and
idle.
idle.
So we can take both actions in both the states.
So can I say this?
Yeah.
So we have this lookup table, can I say?
Yes.
Now, can you tell me any random values for this? Okay. So
No, we have to. These are attributes, right? These are not random values.
yes, that is what I'm saying. So we have to give it the attributes. These parameters are there basically.
Yeah.
These are the features of this.
Yeah. So can we do state and can we add and then can we say attribute is state plus action, whatever the values are there.
Okay, let us take it this. But I'm not getting that how it will this attribute should be dependent, like it should have a role here, like as we are saying that flipping is like flipping gives me a reward, or we can't take it simply like by taking state plus action, these attributes.
Yeah. Okay.
Because say that phi ln, then if I'm not flipping also, this phi is greater, and then my increment this delta theta will be greater, though my value will be lesser.
Okay.
Are you getting my point?
Yes.
So can we take that when we are flipping, this phi is 1 and then this is 0?
Okay.
Something like that.
Yes. No, 0 1 0 1, I think. Flipping
0.
is 0 1 0 1. Achha.
Why? When we are flipping, we are getting the like I'm saying when we are flipping.
Okay, so 1 means flipping, right?
When 1 to 0. Okay. I mean, okay. You are correct. I was in the other 1 is. Yes. Is it fine now?
Yeah. Yes.
So can I say now it's 0.5?
Mm-hmm.
Now coming to episode 2.
No, this entire phi should come there, right? And we should update all these 4 values, right? This phi will go there, 0 1 0 1, and all these theta parameters are updated accordingly, right?
Actually, I'm updating only that particular state and action.
Only one value are updating, right?
So we can add up and we can update all of them.
Yeah.
So
this phi vector will come as it is over there. Phi vector will come as it is over there. And what do we get is this gradient of theta, which is a vector, and we'll add.
We'll add up. But the question here is, like, suppose I'm taking this one state and one action. Like my state is that I'm in the off state and I'm flipping it off. Is okay. So is it required that all the state and action should be updated, or is it like the particular state or particular action
Theta are to be updated. Which corresponds to updating all. I mean, yeah. It's a parameterization, right?
Yes, you're correct. Getting confused. So basically, all thetas actually should be updated. You are correct, absolutely.
Correct. Yeah.
So 0.5 into 1 into 1, it is basically this one. 0. I was in the 0 state and we flipped it off. What about this? It will be 0 only.
Correct. Don't change.
This will this last one. Okay, this one will also not change. What about this?
Will change.
It will change, and what will be alpha is basically 0.5. What will be delta here? Delta is
0. 0.5.
So basically 0 only.
What? All 4 values, right? All 4 values will be there, right? Should not add. It's a theta 1, theta 2, theta 3, theta 4, corresponding to all these 4 attributes.
Okay. Basically, we are updating the features of everyone. So if I talk about this one, I have this 0.5.
Correct.
If I have this one, then we have 0. If I have this, then we'll have 0. And if we have this, basically, this last one, then alpha value is basically 0.5.
Yeah.
Wait a second. I think it's
All alpha is 0.5, delta is 1, phi is 1.
phi is 1, then it is also 0.5 basically.
Correct.
Can I say these are my updated thetas here?
Yes.
Now
Yes.
coming to episode 2.
And now how the like probabilities, these are not probabilities, these are
These are not
values.
probabilities.
So we
Okay.
can have a softmax or like that, and then we can get probabilities
Then
there.
we can update our probability value as well.
Mm-hmm.
Okay, let's not go in detail in that detail. Let's go to let's solve
Okay.
this.
Yeah.
It's fine. It's good that I was also getting confused. Thank you. Like I got to know about like that I was mixing everything.
No, nothing. I mean, we all are learning.
Yes.
Yeah.
So if I talk about this episode 2 here, then suppose though I'll be in state, let's take the same state just for the convenience. Though by flipping I'll be in the state on. Let's take the state off here. So let's again take the flip just to see how it is changing. That is why I'm taking the same thing.
Okay.
And the reward is basically +1. Now, what is the critic's feedback? Now, what is the value function?
The values are 0.5 and 0, right?
Yes.
Value functions are 0.5 and 0.
0.5.
We
Okay, we got it from the last one.
Yeah.
Here we got it this 0.5 basically.
Yeah. V of 0 is 0.5.
V of
and
0.
V of 1 is 0.
Yes. Now, what is how we'll update this TD error? The reward is basically
Yeah.
1
Yes.
plus gamma 1 VS
0.
minus 0.5.
Yes.
That is 0.5 only.
Yeah.
And again, the same procedure will be done.
Yes.
So basically, what the main intuition is that we are trying, like critic is trying to do, like we are trying to do the value evaluation from this and helping the actor to make the decision to update the policy.
Yes.
That is what we are trying to do. Update the policy, update the probability, the thetas are updated. That is how this whole goes.
Yes.
Okay, if we think about in the direction of reinforce, what is the difference when we are talking about only reinforce here and not talking about actor critic? What is the difference between actor critic and reinforce then? Can I say that there we don't have that critic value, that value function is not helping us to update that?
Okay, the value function will come from samples, right? There.
Yeah, that here we are having the both the value function and the policy functions.
Yeah. No, so the in case of normal, I mean, without a critic, the value
Yes.
functions will, or the reward and the value functions will come
Reward.
from samples. The average
Yes.
values and rewards will come from samples.
Yes, basically policy will be adjusted on the basis of the rewards which we are receiving.
Yes. Yeah.
Here we are basically it is based on the feedback from the value function.
Yeah. Yes.
I hope so. This actor critic, some intuition you got it from this example.
Very much.
Let's take 5 minutes break and then we proceed.
Okay. We'll come at what? 7:10, 7:12?
7:12.
Okay. Thank you.
Okay, let's proceed. Am I audible? Everyone is back? Am I audible? Okay. Let us say write two equations and then we'll understand this. Okay, can someone explain these both of the equations? Yes. Come on. First one, you know. Second also, I think we should. Yes. Come on. Give a try. Am I audible first?
Yes, yes, you're audible. Yes, you're audible.
So, give a try. What is this?
So the first one is the del the gradient of the reward policy gradient.
Don't see the left side, see the right side and tell what is this?
That is F. That is the value.
Yes, come on.
What is d pi, madam? D.
I'm saying don't say, okay, d pi, I'll tell you. Actually, the first equation, what it is, like, what is the average reward? You know, what is this expectation? What is the average reward when I'm following the policy pi?
Yes.
This
Yes.
average reward following the policy pi. Now, coming to the second equation, this second, RS of A, what is the okay, starting from this, what is the expected immediate reward? I can say when, what is the reward for taking the action S when I'm in the state S? What is the probability of taking action A? I should move from, okay, left hand side, when I'm in the state S. And then this is a stationary distribution of states when following pi. Basically, what is this? This is the distribution when I'm following the state of the states. Basically, when I'm following the pi policy here, what is the distribution of the states when I'm following this pi probability, like pi here, and then when I am in the state, the distribution of the states when I'm in the state, what action should I perform, and then what is the expected immediate reward when I'm taking this action. This is what basically is the expected, or I can say the average reward. What is the distribution over the states? Then what is the action I should perform? Then what is the reward basically? Summing over states and summing over action. This is what is the above equation. Yes, can someone tell me?
Yeah, so the first equation is from samples, right? And second
Yes.
equation is the same value from model.
Yes. Do you got the whole intuition of the second equation? Can you explain?
Second equation is based on model, right?
Yes, like what is d pi, what is pi of a,
D
like
pi, D pi is a stationary distribution being in
Pi
state
is
S.
policy.
Being in
Pi
state
is-
S.
yes.
Yeah.
So hope you get this equation. It's nothing, just the same equation, the way the writing way is different or the modeling way, like that is expected, I can say. This is basically, okay, I'll get to this afterwards. The gain of policy and pies. First, I'll come with this thing. What is this?
This is just value function.
This is just value function written in terms of Q. We have done
Yeah.
it earlier also many times.
Yes.
Now, taking the derivative with respect to theta, I'll come to the main thing, just going through this way. Just nothing, just a derivative. Derivative of this multiplied by this plus derivative of this multiplied by this. Just simply taking that. Writing it as it is. I'll write it and then we'll discuss. I think I should have told. Okay. I'll write and then. Actually, I missed part and then now I'm realizing. I'll come to the first equation. Just a second. Just like this. A naught basically A pi. What is this Q pi of SA? What I have written basically? If I'm taking action A, what is the how much I can say? This was the average reward we did. I can say how much average reward or how much more than the average reward I'll get basically. This is the RT. Is it correct? Can someone help me with this? Something is wrong.
Madam, the very first equation where you have written Q, where is the reward function there? That is V pi of S is equal to sigma
Just
of A.
Yes. Just I'm writing this V pi with in respect
In
to
Q.
Q pi. Then I'll basically elaborate this Q pi. Then we can get this. Just I'm writing this V pi in terms of Q pi here. That
There is no reward, right? Immediate reward.
When I'll elaborate this Q pi, we have the reward. That is what. What is the difference between value function and Q function? Can someone tell me? Can someone explain this equation, the above equation, how we are writing again? Yes. Can someone help? We have studied the differences between value function and Q function. Yes. Come on.
See, value function is an expected value of taking actions from that particular state, whereas Q is taking an action, expected value of taking an action in state A and then following the policy pi.
That is what we are writing here. You got it?
Right.
Now, can someone tell me what I have written in the last equation? It's getting confusing. Yes. Come on, just try. Yes. Basically, we are writing that if I'm starting with the action A, then how much more than the average reward I'm expecting to get. That is what I'm writing here. Now, coming to the above equation, as we have taken this V pi, we have taken the derivative with respect to theta till this point. Now, after this point, what we are doing, we are writing this first equation as it is. Sorry. We're writing this first equation as it is, the second equation like this, and then substituting the values from this. Rs minus delta pi. And now we are also considering, as it was t is equal to 1 to infinity, now we are considering the rest of the terms, that is the future value functions, like what is the probability and the value functions. We're not writing t is equal to 1 to infinity, that is 0 to infinity. That is why we are considering the rest of the terms here. That is what we are doing in this equation. Now, again writing the first term as it is. Something we have missed. Till this point, everything is clear. Should I proceed? Yes. Any feedback? Okay, let's proceed. Now, can someone tell me how I get through this step? That is what I'm checking, that how the expected value of the return basically is getting cancelled out. Okay. Now, what we are doing here is we are calculating the gradient here, like the derivative with respect to theta here. So it is not dependent on theta. So we are cancelling it out, the expected return basically, that we are cancelling it out. Rest we are writing, we are basically opening the brackets here. That is what we have done, nothing else. Q pi of SA Is my screen visible?
No, no, no.
Wait a second, wait a second. Trying. Okay. Now again, the first term I have written the same here.
Hello.
About the second term, now what I have done is, as I want to know about this delta, wait a second, as I want to know about this thing, I have shifted it to right hand side, left hand side, and shifted this V pi, this one, to right hand side. Rest of everything is same. This is shifted here. Just to know this data, this gain of policy with respect to theta. I'll go it through again. I think some things are getting confused.
Yes, yes, we have to go it again. Yeah.
Yes. I'm also getting confused here only. Okay, we'll go again. Now, after this, what we are saying is, as we know d pi. Now, what is this d pi? What is d pi?
So stationary distribution.
Stationary distribution. Now, if I have, I can say, now what I'm doing is I'm multiplying this left hand side and right hand side. Basically, I'm calculating the expectation with respect to d pi on both of sides. And for if I say that I'm calculating the, let's say this example. You can say that this is basically the sum over d pi of s and fs. The expectation over the stationary distribution, if I'm calculating, that is what I'm doing here. Multiplying by that and taking the sum over that. That is what the expectation. with respect to d pi on both sides. Just multiplying the d pi. It's quite lengthy, so that is why. Now rest is same. I have multiplied by d pi on both of the sides just to calculate the expectation with respect to d pi. So summing over s and d pi of s, basically. Wait a second, I think whole equation is not written. Pi s a summation of s dash p s dash s a v pi of s dash minus d pi s d pi of s, as we know, that is a stationary distribution. Now we have this term. Let us write it. Let us write it basically. What we have in clear sentences, I have summation of s, summation of a, summation of s dash, d pi of s, then pi of sa multiplied by probability of s dash given sa multiplied by this derivative with respect to theta v pi of s dash. This is what we are having. Now, as we know that d pi is the stationary distribution, and when we'll apply on pi or on p, we'll get the same. We'll end up in the same. That is what our stationary distribution state. So that is why I'll get this only d pi into derivative of v pi of s dash. And if we'll see here, that is also the same, d pi of s into derivative of v pi of s. That is why they both cancelled up. And we get the first equation only, which is now this is what is the gain of the policy in our equation, or when we are basically comparing these actions, then what is the gain of the policy we are getting? I was thinking that it will form active critic here. If I say q pi of SA as critic, then the value function, okay. But we don't have the value function here. Okay, let's go through the whole equation, what is happening. I know that it was confusing. I also got confused in between. Till now, till this point, is it clear? Let's start from the starting.
Yes.
Now coming to the next thing. V pi of s is clear?
Yeah, yes.
We have taken the derivative with respect to theta. That is clear. Basically, we want to find the gain of
First equation is clear. It's a simple multiplication.
This first equation is clear. Okay.
Second equation. Second equation.
This q pi of SA, what is the that is what main confusion is.
One equation. No, it's not that. Above the before that.
Actually, the above one is coming from this one only. What I'm doing is I'm just substituting the value of this q pi of SA here only.
Yes.
So what is this? This first, if you'll see this thing, this is same.
Yeah.
This thing.
The first term is okay. Next, second term.
Now the change is here. if you'll see. How the change is here, what is this? If we'll see pi of pi SA, this is okay.
That is okay.
Now, this is the change.
Yeah.
So what I'm doing is I'm just substituting the value of Q pi of SA.
Yeah.
Now, this is the main thing.
Yes.
So what is this saying? That if I'm starting with the action A, I'm given the action A, then what is the this delta pi? We have done that. Delta pi is the expected reward. Then how much I can say the average, how much more than average reward I will get? How much the change from the average reward I get? But I'm wondering how it is equal to Q pi of SA.
Why this summation term is added over there?
From t, if I'm starting from the action A, from t is equal to 1 to infinity, I'm summing it up that how much.
Madam,
Yes,
very
yes.
first, madam, the very first, somehow I am not getting convinced, madam, that the P pi versus Q of S comma A, that sigma, yeah, that very first equation. Can you just
Can someone explain, help me in explaining that?
Yeah, you have simply said that the value V pi of S is nothing but sigma of a Q pi S comma A. Okay, taking that probabilistic averaging. I think we are missing some immediate reward function. What I feel.
Can someone explain this first equation? Yes. I'll come to the next one. If someone has understood, please.
This V pi S. V pi S.
Yes,
Which
yes.
equation?
V pi S. V pi S.
Yeah. The thing is, this is the value function of a state, and if we take all these actions in state S, what are the value? I mean, and then sum over all these action value functions, Q pi S A. So you'll get value function S as per policy pi.
No, that's true, but the immediate reward function is missing.
That is Q pi of S only. If we'll elaborate the Q pi of S, I'll get the immediate reward. I'm just writing Q pi of S. If I'll explain what is Q pi of S, that will contain immediate reward.
Okay.
I have just written Q pi of S. Is it clear? You told me like what is V pi of S and what is Q pi of S. What you told me is the same what written in the equation.
Yes. Maybe if you write a Q pi of S comma A on the left hand side, it will change, right? So
can someone elaborate what is Q pi of S?
Q pi of S comma
Q pi is the action value in state S and action A
is equal to maybe similar equation, madam. Can you write Q pi comma A is equal to what?
You tell me, like we have done what is Q pi of S? The reward plus the immediate reward plus, yes.
Plus value plus gamma of that value function, gamma of that V pi. Yeah, gamma of V pi.
Then
of course.
Yes, but then you know what is the difference between value function and a Q function? You told me that we are taking the first action, we are considering in the one, we are not considering the first action. That is what just Q pi, I can write in the intermediate, like the reward function and all, just I am writing this Q pi. Just because we have to go many steps, so I'm not elaborating here. I think you got the point, like how the reward plus the immediate reward will come in this Q pi here.
Okay, ma'am. So it takes time to sink in. Okay, but I see my understood.
Yes. Yes. I think you said something. Am I audible?
Yes, you're audible.
Okay, madam, go ahead.
Okay, where were we? Yes.
This third term added no over there. How this third term has appeared? That summation S prime and transition probability V pi S prime. This term.
This term is basically, now I'm saying is equal to t is equal to 1 to infinity. Now here I'm not saying t is equal to 1 plus 1 to infinity. What we do when we calculate this q pi, we are taking the future aspects. That is what I'm taking the, what we do, the summation of as he told, the reward plus like the transition probability into v pi value function. That is what I'm doing rather than writing t is equal to 1 to infinity. Either we can write it like this, or either I'm considering here the future basically value functions. The rest of the term I'm considering here. I'm not writing this basically here. You got it? Is it actually clear? If we think about this, if we think about this, what is this? We are considering when we write the q pi of SA, I'm not writing t is equal to 1 to infinity, which means I have to consider the future value. When we are writing this, we have to consider the future values as we have to see the future and check that the transition probability into v pi of S dash. That is what I have written.
Okay, so this is bootstrapping, right? It's bootstrapping.
Boots.
So this RSA plus this value, right?
Yes, yes.
Minus,
Bootstrap.
is it bootstrapping?
Yes, yes, because we are bootstrapping is considering the previous one. If I'm not
S prime is the next one, right? Not previous.
next one here.
Yeah, next one. Yeah.
So
S prime is the next state, right?
Next state. If we think that what we are doing is S and A we are, then what is the probability of S dash?
So,
And then what is the value?
in this q pi SA, it is summation t running from 1 to infinity expected value.
Yes, yes.
So if we take this expected value inside, expectation of RT is RSA, right?
Yes, yes, yes.
Yeah. And then expectation of rho pi is rho pi because rho pi is constant. Right?
Yes.
Yeah.
And then
And
this
then t running from 1 to infinity, and then that expected value from
this converted to this. We are considering now the future value.
Okay.
So that is what. Till this point, now it's somewhat clear.
Yes.
Now coming to the next thing. Okay. This is okay. Q pi of SA plus pi. Then I also have to check because it's so lengthy. Okay. Now I am taking the gradient, derivative with respect to theta. It is not dependent on, the reward is not dependent on whatever the parameter I'll take. So that is why it's 0 basically. Just that is what I have done. It's 0. And then the derivative, the same I have written, nothing else. Written it as 0. Is it okay? This step is fine?
Yes.
Okay. Now coming to the next step. I have shifted this term to the left-hand side and taken this v of theta, v pi of S, this to right-hand side. Is it fine?
Yeah.
Now, we again can do this stationary distribution. Now, stationary distribution, if I say that here, I say that I have a stationary distribution, steady distribution. I can write this expectation as this one. Just I am taking the expectation on both of the side, left and right hand side, with the distribution d pi with respect to d pi on both of the sides. So multiplying like this expectation. So that is what I have written here. Multiplying by both of sides, like sum of S, d pi of S, multiplying left hand side and right hand side. That is what I have done here. This page. Here. Is it clear? Multiplying this both left hand side, right hand side, and summing it over S, which means that expectation with respect to d pi on both of the sides. With this distribution, taking the expectation on both sides, is it clear?
Yeah. Yes.
Okay. Now coming to this. This was the third last term which was coming. This was it, summation of d pi s, pi of s. And we know that the stationary distribution, if I'll apply on pi or p, I'll end up with the same thing. That is what the steady state distribution or stationary distribution comes. So when I'm multiplying with pi of SA or probability of this one, I'll again end up with d pi of s. If I'll again end up with d pi of s, these both terms are same basically. So they cancelled out. So we get this performance parameter, the gradient of this change of the performance parameter. Basically, that is what it is shown here. Now I was thinking that they'll end up in the critic somehow. They gave this derivation, actor and critic. I was thinking that q pi will be the critic here. Yes, though q pi is the critic, but how is the value function be the actor here? Okay. Are you getting what I'm trying to say? The actor and critic terms, which I was saying, like we'll have the value function and as the critic, like earlier we have done that actor is the policy and critic is the value function.
Yes.
But what I am observing is, okay, it's fine. I'm getting the critic as q pi of SA. Q pi of SA is helping me in improving the performance and gain of the performance, but V pi is not. You got this derivation?
Yeah.
Okay. I thought that I'll cover this. In the starting of the lecture, I was like, okay, we'll consider cover this type of optimality and hierarchical array as well. Okay, maybe this function approximation.
Yeah. So here, thing is, I mean, the further thing that he has mentioned, no, so to approximate pi and q by function approximation,
Okay.
where pi is approximated by theta and q is approximated by w, and
Okay,
then
function approximation. I was thinking that maybe he'll cover the function approximation and I'll hierarchical RL and all. Okay, let's go with this. Q pi of SA. Q is parameterized by
w.
W. So the parameters W are representing the Q function, and there's some parameter, I can say theta representing the policy here.
Madam, on a general question, this function approximation for q pi and v pi is similar, right?
Function approximation is okay. Like we'll do the function approximation now, but what is function approximation? You asking what is function approximation?
No, I know what it is. We can apply it to both to v pi as well as to q pi, right? So we can attempt either v pi or q pi approximating. No. Just to clarify, something is gray in my area. Like I always thought that these value functions v pi and q pi, if from any one we can get the other one. So when you're approximating, you can start with v pi and approximate function approximate function v pi, or we can approximate q pi. Okay, I don't know. Please, yeah.
Can some answer like can we function like as he's saying that can we approximate q pi from v pi and v pi from q pi? Yes.
The attributes for v pi and attributes for q pi will be different.
Yes. How? Because the actions or
actions are there in q pi. Actions are there in q functions, which are not there in v functions. Yeah.
Yes, the first action which is there in q function is not there for the v function, so it may be different there.
Attributes are different also.
Yes. Now coming to this function approximation here. So some like Q is parameterized by W, some parameter theta basically for the pi here is like parameter theta I can say that is represent the policy, I can say. Now if I go about the error, when we are going about the function approximation, I get the error. Let's see about this error. What is this error basically? What is this? What I have written?
Squared error function.
Squared error function, the true error, the true and the predicted one, basically the difference between them.
Yes.
How can I basically minimize this squared error?
Gradient descent.
Gradient descent, basically. Can I say we can change the weights in order to minimize the squared error? That is the weight.
Yes.
I'm taking the gradient by SA minus 2 we are not considering when we are taking the derivative. So do I want in the direction of the gradient or opposite the direction of the gradient?
Opposite.
Opposite direction. Why? Error we are computing.
Minimize the error. Yeah.
Minimizing the error. That is why we want to get it the opposite direction of the gradient.
Yes.
Now, so if I'll run for the long time, then what is the probability I'll end up in S is basically, I'm taking this stationary distribution, state distribution. Wait a second. We'll come through it. What I have done here, now I'm considering this SA, what I have done here, if I'm choosing like pi of SA,
We are at a plateau where gradient vanishes.
yes, and what do we want? That it should be equal to 0. That is how I can say the value, it will converge basically. That is our main motive here. That is what we're trying to do. About the proof, actually, I have also not studied. That is why I was saying this is the main overview. Maybe in the next lecture he can explain the proof and all. I think the professor has given that how it is happening. How the error is 0. Basically, some conditions are given. I think I haven't gone through that. Basically, softmax function and the derivative. I think.
Yes.
Is it like that? Maybe in the next lecture he can. I'll ask him for this function approximation thing to clear it more clearly. If still you have doubt, we can go in the next lecture as well. So should I give the overview of hierarchical RL or so, or we'll proceed in the next lecture? It's up to you, like types of optimality, hierarchical RL. Just the overview.
Yeah. Please give overview so that we can solve the assignment.
Yes. I'll complete this hierarchical RL and because so that he can also proceed with the completion of this week so that you can complete the assignments, and moreover 2 lectures are after this. So what is the reason we went for the function approximation? First thing. Yes.
To reduce the a value function table, okay, to parameterize so that we can approximate the value function with a parameterized function so that the storage is less. Because state space is huge, yeah. So yes.
So basically, in short, I can say that state space is large, and we want to scale up for the larger problem. So that is why we come up with this function approximation. And basically, here what we are going to do is we are going to find a structure. Or in function approximation also, we are basically generalizing. We are basically finding a structure. We are having that like. We are representing the policy like a structure we are repeating again and again, then finding a structure, expecting the values which are closer to each other through this ways. Now in hierarchical RL, what we are saying is, instead of repeating it over and over again, we can think of the sub problems that we are solving over and over again. When I have larger problem, then I'm dividing into the sub problems so that I'll solve these sub problems. And when it is coming again, then it will be helpful to me as I'm optimizing them. Okay, let's go step by step. Example, if a game is there, if the small moves are there, I'm trying to solve that small moves so that I can solve I'll try to have a huger picture. I can try to solve a larger game, but first I'm focusing on the like smaller moves there. Now the other example which the professor gave, like suppose you are going to a central station, you have to minimize the cost. Then what is the thing that how you'll go to the main gate? What I'm doing is I'm dividing the main problem to the sub problems. Then how I'll go to the main gate, the problem. Then what is the problem? Like I have to solve this long horizon problem. For this long horizon, I'm solving the sub problems. That is what I'm doing here. Or I can say it as temporal abstraction. Now, if I say I have to
Madam, it reminds me of the same concept in dynamic programming.
Can I say instead of dynamic programming, divide and conquer?
Divide and conquer. Okay. Yeah, it is not recursive. It is linear divide and conquer. Okay.
Am I correct? Maybe what are the other what others says about this? Can I say that we can relate it with divide and conquer?
Yeah.
Somehow.
Yes.
So suppose, as professor said, that if you want to go to railway station, first you have to go to the main gate. So and then when you have to go to main gate, you have to turn left or so, and then how you will walk or so. Basically, we can divide into numerous of sub problems, and then so that it will be easier to solve the larger problem in abstract way. And temporal abstraction, basically each one will take different amount of time as well. Turning left will take lesser time, whereas going to some main gate will take the more time. Now coming to the definition of hierarchy as well, what we are doing, many small sub problems are there. We have to solve them small sub problems, and then we are getting it to the big problem. That is like we are putting it together, and then we are getting the we're solving all the sub problems, and then in the whole way we are solving that big problem. That is what it is there, and it is up to us, like basically how deep we can go. That is there, and the other sub problem examples were like given in the class, like if a player is there, obviously the level of optimization. As optimization, more we'll do, more we'll optimize, I can say. In the real world, if you use again and again, better is the optimization. If you're playing the same game, if you're playing the same shot again and again with the same precision you can do, with the better precision you can do, that is what Now, is it required to optimize everything, or is it not required to optimize every sub-problem? What do you think about that? Yes.
Sometimes he said like we need not optimize for each sub problem.
Maybe we are using it once, that's why. Can I say?
Yeah.
Also, if you're using not many times, it's okay not to optimize every sub problem there as well. Now, the other term coming is ability to transfer, the advantage of hierarchical RL. So can someone explain me what do you mean by this ability to transfer? By the name itself? Yes.
The similar sub problem might appear in other bigger problems which we can reuse. The solution can be reused or reapplied.
Absolutely correct. So basically, I have small problems. You are solving it, and then completely different problem is coming, but somewhat related problem also. But there might be something like from the smaller problem which you have solved already, and we can reuse it. That is what is ability to transfer. And can I say by this thing, hierarchical RL basically gives us more optimized technique, basically modules, basically, so that we can help to optimize. Or I can say the usability is there in the other end. Now, the other aspect comes planning. What happens in planning is, can someone tell me, is it related to hierarchical RL? Is it also like reusability optimization, or is it totally different? Yes. Basically, in planning, what they say that they are planning is a technique like we are happy to find a solution here. We are not optimizing the things. We are happy. Okay, it's fine to find a solution. What are the preconditions? What are the post conditions? The professor has given the example. Like if I'm putting the phone down, let's say we are not stacking it down. Then what is the precondition? Is the table empty? Post condition that after that the table will be free or not. That is what basically planning means. We are not we are only focusing on solving the problem here. But what is the con here? Like what is the drawback here? It depends basically whether you are on the problem also, but what can be the drawback here, or what can be the advantage of hierarchical RL? Now only we studied. Can I say that if we are optimizing a sub problem, or we are optimizing them, then we can reuse it. If the same thing occur again in the other problem, as you told, then we can't reuse in planning. Something picking or putting also, if I have optimally done one time and other time also it came, I can basically do it better, or I can choose that path optimally. I'll be optimally better because I know how to do that. That is what is the advantage of hierarchical RL here. That is why we are learning here, and why not we are doing the planning here. We have the transfer ability to transfer or reusability here. And coming to this also, I have the abstraction also here. If the main gate example was also there, one more thing is there. Suppose the main gate example is there, railway station example. I have to go to railway station. I'm going to the main gate. Now I'm not considering the aspect that which platform I'll stand in that railway station. The main focus is how to go to the main gate. So basically the whole bigger problem is I'm not considering all the state spaces. It's not humongous to me. It's not, there are no extra variables, such a huge load of extra variables. I'm ignoring these variables the time I'm going to the main gate. I'm ignoring the variables that how I have to stand the platform when I'm getting out of my building. So basically it is more easier to a simpler problem to us to solve. And on the other hand, it is basically I can reuse also. So it is, I can say it is more efficient learning, I can say. Do you got the overall idea what is hierarchical RS? Yes. Yes, come on.
Yeah, somewhat. Yeah.
Somewhat or clear? Basically, it's nothing, just we are dividing the problem into sub-problems, because now that sub-problems can be reused also. And obviously, if we'll divide a huge problem into sub-problems, now I'm focusing on that sub-problem only. Now I don't have that humongous or huge thing to solve. Not in that thing, I don't have so many extra variables also. I have that limited variables for that sub-problem only. Is it clear?
Yeah. Yes.
Now, talking about the optimal, we have we have this hierarchical optimal, flat optimal, recursive optimal here. Or I think the example was also given from room 1 to room 2, or it was given which policy is better. Okay. So first I'll go, what is hierarchical optimal? Basically, we have to respect the hierarchy, but each component, it's need not necessary that we'll solve it optimally. I'll write 3 of them. So what do you think that what is the difference between this? These 3. Which one is better?
Flat optimality is the base.
Flat optimality. Why? What is, first of all, what is hierarchical? What is recursive? What is flat optimal?
Flat is global optimal, solving entire problem.
So it's is there any structure that I have to follow in flat optimal?
No structure. Yeah.
So basically, in hierarchical optimal, I have to respect the hierarchy that I have to go. But each component need not be optimal here.
Yes. Yes.
Recursive optimal is I come with solution where individual components are solved optimally. Then overall components are obtained like by taking them together. Flat optimal is like we are not we are not considering the hierarchy here. Basically, that is what is global optimal, or I can say flat optimal here. It gives more optimal solution than hierarchical and recursive. But sometimes we have to solve like follow the hierarchy. As the first step is this, the second step is this. We can't go as such here. If I talk about this recursive and hierarchical, then which one is better?
Hierarchical optimality.
Why? Like as we have can you tell me why?
Sometimes I mean this all these substructures which are optimal might not lead to optimal kind of solution.
Yes, yes. Like sometimes the sub problems may not lead to an optimal solution. As an example is also given, like sometimes 2 problems are there, they both are optimal, but when we consider the whole problem, then it's not an, when we consider this sub problems together, they might not be optimal there. That is what hierarchical, recursive, and flat optimal is. Is it fine? So in the next lecture, do you want this to be repeated tomorrow, or I should tell him to proceed further and first of all function approximation? he'll cover, and then like
Yes.
so you want that after this you will go to semi-MTP or okay. Maybe the next week we'll try to cover the semi-MTP and the functional approximation as well. The next lecture, I want that I should take form DP, but so that I want that 2-hour lecture should be of form DP. It's an interesting topic, basically, partial observable Markov decision process. Here, it's like we can't see the action of the other person, or so partially observable it is. Okay, let's see. And the last one, I want that we should have a revision here for all of them. And I want that you should tell in the Slack prior only like which topics to be focused more, or which problems I should take in the last lecture so that it will be easier. Okay, thank you.
Thank you.
Thank you, everyone.